we normally consider up to this point. On the other hand, we might have a function, for example, z is a function of two variables x and y. Now, this means that the independent variables, we have a pair of values. What we write normally is x, y belongs to not real numbers, but real numbers squared, which means this is the set of all pairs. This is the set of all pairs of two real numbers, ordered pairs, of course. It's important which one is the first number and which is the second number, and this. So we write it like this because r squared, by that we understand the coordinate plane. So normally now we have this coordinate plane, for example, the surface of the desk, which has coordinates x, y, and for each point in that plane that has two coordinates x and y, the function has one specific z value. So in this case, the graph of this function would be a surface. For example, we can imagine the domain could be some region of the xy plane, like well, it looks like a puddle during rain. And for each point in x, y, in the xy plane, the function value is some value of z, a third variable. The dependent variable z depends on those two, which actually obviously denotes the height of the point. So if for all these points of this little region perhaps in the xy plane, we have one specific z value, we might imagine the graph as some surface, for example, the roof of some pavilion or some tent, like this. So we have an area in the plane, but the z values don't have to be all the same, so that the surface could be curved or spiky or having gaps, all kinds of things. So the graph of a two-variable function is a surface. It is, of course, possible to think of functions in three variables. For example, for this one, we could have, for instance, z equals x squared plus y squared, something like this, for example. This would be what? Not exactly. But well, basically, yes. If z is positive, then yes, we could have a sphere. If I have z squared, then I might have a sphere with the center and the origin, for example. Or we might have something else. I might have z equal 2x minus 3y plus 5. This would be a plane, because if we rearrange this, we get the traditional Cartesian equation of a plane. 2x minus 3y minus z equals minus 5. That's an equation of a plane. So it could be a flat roof, perhaps oblique, not exactly horizontal, but it could be anything. And in a similar way, we might have a function, for example, w is a function of x, y, z, and we can imagine this any function that has a different value, for example, in different points of space. For example, we might have, this could be a distribution of temperatures in this room. If x, y, z are the coordinates of any point in this room, in the space of this room, not just on the floor, but anywhere in this room, then W could be the temperature at that point, for example, or the intensity of the electromagnetic field, for example, but that's a vector actually, because that has a direction. We might have functions. So we might have functions, we will discuss functions depending on several variables but producing one dependent variable. It is possible to have one independent variable and to produce several values, to produce a vector at each point. We might have a vector. We might have functions depending on several variables and producing a value which is a vector, again three different variables, each of which depend on x, y, z. Those are called tensors. horrible things, although mathematically quite fascinating. So, in general, we will discuss functions in two variables. Functions depending on two variables, and the third variable is the value that depends on the first two. But generally, we might have as many variables, as many independent variables as we like. So the generalization of a function, we could have y equals 3x1 plus 4x2 minus 5x3 plus whatever, 1 over x4, 4 not to the fourth power. So these are simply examples. We might have anything as long as it's one variable which is dependent on some other variables. 2, maybe 3, maybe 4, so there are endless possibilities. But for better understanding, we will only discuss functions of two variables, because they are basically what make most sense. The graphs of those functions are surfaces. So if this is a point x, y, then this value obviously is the corresponding z value, the height above the floor, if you like, the height of the surface, the coordinate of the vertical coordinate of that surface. So this is, I would say, the easiest way to imagine two variable functions. The functions in more than two variables are just more difficult to imagine and impossible to visualize. At least function in two variables, we can try to imagine what the graph looks like, what the surface looks like. So the domain is obviously some subset of the real number plane, consisting of points in the real number plane. That's the general domain. But again, it depends on the function. Some functions have limited, or actually we might say many functions have limited or bounded domains. And one of our tasks today is to figure out how to determine, how to describe a domain of a two-variable function. Can we write an equation for that domain? Can we write any other kind of description? Can we write a formula? It turns out that we cannot. Then how can we describe this domain? We can sketch it, and we'll do that. What else? What else about two variable functions? Homogeneous functions, right? Homogeneous functions. If we talk about two variable functions, then...
Wait.
Yes?
Mechanically.
For example, if we are talking about the function z equals function of two variables x and y, a function is called homogeneous if, when I multiply both variables by the same constant, I get the z variable, which is the same constant to some power, times the original value of the function. In this case, the function is called homogeneous. In other words, if you multiply both the independent variables x and y by some constant, then the function value is also multiplied maybe by the same constant, or maybe by the same constant to some power. For example, if I'm talking about that function I had as an example, this function, then obviously if I multiply both variables by the same constant lambda, I actually get lambda squared times the original function value. So this is a homogeneous function. Obviously, because we get the original function times lambda to some power. Basically, it means that in a way you might say that x and y are in the same power to some extent. You might say that. It's not necessarily always a power, but sometimes you might say that. So in a way, they are similar, perhaps. They have a similar weight or similar density, if you like, to some extent. So homogeneousness is a bit difficult to define normally, naturally, although I do hope that in high school you were familiarized with homogeneous equations. For example, homogeneous equation in two variables, something like this, or homogeneous trigonometric equations, perhaps yes, perhaps no. For instance, 3 sine squared x minus 6 sine x cosine x plus cosine squared x equals 0. That's a homogeneous trigonometric equation because the power is the same all the time. The total power of each term is the same. But that's only a particular case of homogeneousness. So in reality, the homogeneousness is best defined this way. Then you don't have to talk about powers of terms, especially if the terms are not powers by themselves. What else? Let me think. What else do we need? Limits, probably. Yes, limits. A limit of a two-variable function. What is that? So, for example, we have this domain, which is a subset, which is some subset of the xy plane. And in this domain we have a point x0, y0, and then we say, okay, let's suppose the independent variables tend to this point. So x value tends to the x0, y value tends to y0. How do we describe the limit of the function in this case? In the single variable functions, that was simple. We simply took the x-axis and we made the x values approach that point, and we were looking at what does the function do, where does the function tend. Single variable limits were simple. Now what do we do in this case? We might write limit as x tends to x0 and at the same time y tends to y0 of the function xy. It could be written, how do we print this? What do we do there? We don't, well, in many cases, it is possible to think of both of these conditions at the same time, but it's not always true. It's not always true. So generally what we do, we write it as a repeated limit. We could write lim as x tends to x0 off. Limit as y tends to y0 of this function, like this. So first we find this limit, we think only about the change of the y variable. We find this limit, so we imagine that x is constant, x is fixed. We only consider the change of y. Then we have some expression there, and then we say, okay, now let's assume that x is changing now. Or we could do it as a repeated limit in the reversed order. We could start by finding the limit as x tends to x0 of this function. And then, when this is established, and it will be an expression in terms of y, when this is established, then we can take the limit of that as x tends to, as y tends to y0. This is actually an important thing because it is similar to what we'll do with double integrals. Again, we'll think about the order of integration, about the boundaries of integration with respect to one variable, with respect to the other variable, but we will do them just like this, separately in terms of x, and then afterwards separately in terms of y, or in reverse order. So this limit can be found as a repeated limit. And if you have any doubts, the limit exists if and only if both these limits exist and are exactly the same. If they are really the same, if they both exist, this exists, and they are the same, then we can say that that is the limit as x tends to x0, y tends to y0. In other words, if we have a point in the plane towards which we want to tend, we don't go at any random, by any random trajectory or just at random as in random. So we approach, for example, the specific y value. So the specific y value can be approached like this, but because it's the line for different x values, it will be an expression depending on x. And then along this line we can approach y. Or the second order could be we start by approaching the specific x value, and then we have a function described on this line. And then we move along this line with the corresponding y value, and again it has to be the same. So limits in two variable functions are a bit more difficult to imagine physically, but the thing is that we don't do it in a random situation. So we first of all we approach the specific value of y, and we imagine that we are doing it everywhere on this line. And then when we have established what the function looks like on this line, then we move along this line and move towards that specific x value, or the other way around. Sometimes, of course, we don't need to do this because it's obvious that you can allow to do these two things at the same time. Sometimes it's very obvious that these both limits will be the same and the limit exists. But sometimes, especially when we have suspicion that the limit might not exist, we have to do it this way just to check what's going on there. Alright, now let's have a look. Let's have this example. Function of x and y equals 2x squared minus y squared divided by x, y, and let's have a look. So determine the domain. Obviously this function is defined for all x and y values except what? Except the axis of coordinates. X cannot be 0, y cannot be 0. So we might even sketch the domain. The domain of this function is the whole coordinate plane except for the axis. The domain of this function, x and y, can be any value except for 0. So all these points belong to the domain, all these points belong to the domain, all these points belong to the domain, and all these points belong to the domain. Only the points that are on these two coordinate axes do not belong to the domain. That's why I represented the axis by dashed lines, to stress that they do not belong to the domain, and all the other points do. So the domain is the whole real coordinate plane except for the axis of the coordinates, and obviously the origin. So that's the domain. Now find function value of 2, 1. F of 2, 1. What do? We simply put 2 for x, 1 for y, so I have 2 times 4 minus 1, 2 times 1, so it's 3.5. So we can find the function value at each point like this. I'm not going to put the next one, 1 minus 3. If I put minus x minus y, I get exactly the same value. So we can say that, we don't say that this is an odd or an even function, but we understand that there's some kind of symmetry. If I change both signs of x and y in this function, I will get exactly the same function. Which means that if I go in opposite directions, there's the symmetry. So there's some kind of symmetry with respect to the center of coordinates, to the origin. At least horizontally, when we are looking at the xy plane. 1 over x, 1 over y, composite functions, like composite functions. We put in f of 1 over x, 1 over y. This is a composite function, where we have the function f, and then each of the variables x and y actually is becoming is becoming a function. So in a way, this is a composite function. So now if we put in the corresponding values in there, we get 2 over x squared minus 1 over y squared divided by 1 over xy, and you might want to simplify. So you would get 2 2y over x minus x over y. Like this, I think. No? Yes. No. The squares disappear. The squares disappear. Okay. Now let's prove that this is homogeneous. For that, I'm writing f of lambda x lambda y, where lambda is any random constant. I get 2 lambda squared x squared minus lambda squared y squared divided by lambda x times lambda y, and we can see that lambda squared actually cancels out. And we get 2x squared minus y squared over xy again. Which means it's multiplied by lambda to the 0 power. It still corresponds to the idea of homogeneousness. So this is a very basic kind of homogeneousness. We can imagine that it's multiplied by lambda to the 0 power by 1. So it's still homogeneous, yes, lambda to the 0 power. It's not lambda squared, it's not lambda, it's lambda to the 0 power, because lambda simply disappears. The same thing. So this means an interesting thing, the homogeneousness of this function, this kind of thing. So if I multiply lambda x, lambda y, in other words, if I move on lambda times further in the same direction from the origin, the function remains the same. In other words, if I move in the basic plane, in the xy plane, if I move along a line passing through the origin, so if I have this xy plane like this, so anytime I multiply both x and y by lambda, I'm actually moving along this line. And it seems that when I move along this line, the function value doesn't change, which is actually something very interesting. So on any line like this, drawn through the center, the function value is the same. So the graph consists actually of infinitely many horizontal lines. That's something worth considering. Now, the next example, the domain of the function 25. So f of xy is square root 25 minus x squared minus y squared. How do we find the domain of this function? The square root exists only if the radicand is greater than 0, well, it's non-negative. So 25 minus x squared minus y squared must be equal to or greater than 0. Otherwise, the square root will not exist, which means x squared plus y squared has to be less than or equal to 25. What kind of inequality is that? If I have x squared plus y squared equals 25, what would this be? What is this? It's a circle. It's a circle with radius 5 is this circle. Now, if the sum of the squares, x squared plus y squared, is less than 35, then it's inside. So I can see that because this is the circle itself, this describes the distance of the point is less than 5, obviously. Remember, the distance of a point from the center, remember in vectors, is the square root of x squared plus y squared. So the distance of a point has to be less than 5, which means the point is inside the square, inside the circle. So this means that the domain is a circle, including the boundary, because on this boundary on the circumference, the equality holds, which means the square root, it's the square root of 0 actually, it exists. But other than that, the domain is just this circle. And this is how we will depict domains of these two variable functions. We will show them as regions in the plane. We will simply show them in the plane, we'll sketch them. That's the only way. Because of course I can write this inequality, but if this inequality is more complex, it doesn't tell me what it looks like. It doesn't actually describe any relationship between x and y. So the best way of finding the domain is sketching it, depending on the conditions, depending on the constraints. Alright, some limits, and then on to the exercises. So limits can be bad or nice. I didn't put the nicest ones here as examples. Alright, so the limit of x minus y over x plus y when x tends to 0 and y tends to 0. Well, remember, if both x and y tend to 0, we have 0 divided by 0. If we try to do both the limits at once. If I want to do both things at once, I have 0 over 0, we know that that's an uncertainty. You can divide 0 by 0, but it can be anything, and we don't know what. So in this case, we have to work them in separate orders. So let's do, first of all, lim when x tends to 0 of lim when y tends to 0 of x minus y, x plus y. So if y tends to 0, we start with the inner limit. If y tends to 0, this limit is what? If only y tends to 0, we get x over x, which is 1. So I have limit when x tends to 0 of 1, which is 1. On the other hand, if I look at it in the reverse order, if I start by letting x tend to 0, no, minus 1. See, if x tends to 0, I have minus 1. Lim of minus 1 when y tends to 0 now. So it's minus 1. These two limits are not the same. So I can say that that limit does not exist. It does not exist because these two limits, if I go at that point this way or if I go at that point that way, are different. They are not the same. So if I move like this, I tend to 1, and if I move like this, I tend to minus 1. That's already clear that this limit does not exist. The next one, what made me put these horrible limits there? They really look awful, right?
Yeah.
Lim, when x tends to 0, y tends to 0, of 2x minus y cubed times sine 1 over x plus 2y, like this. So now, in this case, we are not going to do repeated limits. But we are going to consider what's going on. If both x and y tend to 0, this one, 2x minus y cubed, tends to 0. So I can write lim x tends to 0, y tends to 0 equals 0. On the other hand, sine of 1 over x plus 2y. What's going on if x and y both tend to 0? This value tends to infinity. Sine of infinity, what's that? What does that mean?
We don't know.
We don't know because we know how the sine function behaves, right? It fluctuates all the time. It doesn't have a limit at all. But it's bounded. It is always less than or equal to 1, greater than or equal to minus 1. And so actually I can say it's something infinitely small multiplied by something at maximum equal to 1. That will be something infinitely small. This limit will actually be equal to 0. Because we could use the squeeze theorem, or sometimes called the sandwich theorem. This limit is obviously between lim 2x minus y cubed times 1 when x tends to 0, y tends to 0. On the other hand, it's greater than lim 2x minus x cubed times minus 1. But in both cases, this limit is 0 because when x tends to 0 and y tends to 0, we can see that this first factor tends to 0, no doubt. 0 times minus 1, so this limit is 0. There, 0 times 1 is 0. So if something is between 0 and 0, 0. So we can solve this problem this way. So sometimes this is what we do, because we understand that sine of something, if this something tends to infinity, the sine value is actually undefined because it keeps changing all the time. It keeps oscillating between minus 1 and 1. And so we simply take the extreme values of sine. We simply take the extreme values of sine. And that's it. This was not, let's say, mathematically, technically, fully correct or fully, let's say, polite mathematically, because actually when x tends to 0, y tends to 0, we don't exactly know whether 2x minus y cubed is positive or negative. So the sign thing was a little bit shaky. Let's say I cheated a little bit. But the general idea is the same. The general idea is the same. And so the final one, when x tends to 2 and y tends to 1 of sine x plus 3y minus 5 divided by x plus 3y squared minus 25. Looks awful. Unless you pay attention to what you have there, you have a difference of 2 squares in the denominator. You have the difference of squares. You can factorize it as a difference of 2 squares. A plus b, a minus b. So if I factorize this, I have sine x plus 3y minus 5 divided by x plus 3, 5 minus 5 times x plus 3y plus 5. But I'm going to write that other part separately, x plus 3y plus 5. So a squared minus b squared is a minus b times a plus b. I'm using the formula for the difference of squares. And I wrote the sum separately outside. Why? First of all, because I noticed that this is the same expression. Secondly, because this, when x tends to, sorry, it was y, when x tends to 2 and y tends to 1, this doesn't tend to 0. So this fraction doesn't tend to infinity. That's fine. It's a finite number. The limit of this is a finite number. Now what happens to that part? When x tends to 2 and y tends to 1?
This one will be.
It will be 1. Because in this case, the limit x plus 3y minus 5, if x tends to 2, y tends to 1, is actually 0. Which means it's sine t over t when t tends to 0. This actually is this.
One.
because we have sine of something that tends to 0 divided by itself. It's 1, right? So this limit is 1, and this limit is it's 10. All right, so that's your limit. So you see, it's not always strictly necessary to do the repeated limits. The repeated limits are important when we have uncertainties. When we have uncertainties, when we can't actually decide how to solve this. Sometimes, as you see, the repeated limits are not quite necessary. All right, let's get to the exercises. Find the values of the given functions. I think I can leave that for homework. I can leave exercise 1 for homework. I think that's simple. You simply put in the values for x and y and you find the function values, right? So exercise 1, I think, is not something that we need to do on the board. What about exercise 2?
It's also the same.
It's similar, yes, you can do that at home, that's not a problem. Or if you need it, then we can do it here. Prove that the given functions are homogeneous. 4 of them. Which one?
Third one.
Number 3?
Yeah.
Okay. Let's do number 3.
Not so hard.
So 3, 3.
I hope it's the last topic.
Function of x and y is x squared minus y squared divided by y square root x squared plus y squared. I think it's quite obvious that we will have lambda squared on top, lambda here, lambda squared under the root. When we take it out, we get another lambda, lambda squared, lambda squared. So this should be very simple, actually. This should be very, very simple. Now, if we look at perhaps 2, so 3, 2 is function 3x squared y minus square root x to the 6th minus y to the 6th. So f of lambda x, lambda y is 3 times lambda x squared times lambda y minus square root lambda x to the 6th minus lambda y to the 6th. What we do is simply put lambda x and lambda y instead of simply x and y. And here we have, this will give us lambda cubed times 3x squared y minus, here we have lambda to the 6th power under the root, the common factor. If we take it outside, it becomes lambda cubed. So it's lambda cubed square root x to the 6th minus y to the 6th, which is lambda cubed times f of xy. So yes, it is homogeneous. It is homogeneous. In this one, we would get the same, f of xy, so lambda to the 0 power, lambda to the 0 power, so that's not a big problem. Now the domains. The domains are the most important things today. So if we consider the domains, we have 1, 2, 3, 4, 10 functions whose domain we want to see. Exercise 7 is missing because obviously it remained on the 3rd page somehow, so okay. Alright, the continuity of the functions remains for next week. Okay. So exercise 4. Sketch the domain of the function if it's given by x is between 0 and 1 and y is between 0 and x. Alright. So if we see these double inequalities, we have to understand, let's consider the boundaries. X is 0. What is that? X is 0. It's the y-axis. This line, the y-axis, is x equals 0. X equals 1. Obviously, x is 1. Is another vertical line. This is x equals 1. And if I say x has to be between 0 and 1 for all points of the domain, I have to say that all points of the domain have to be between these two lines. If x has to be greater than or equal to 0 and at the same time less than or equal to 1. Obviously, the points of the plane corresponding to this inequality are these points between those two parallel lines, parallel vertical lines. Now, the second, y is greater than or equal to 0, all right? Only positive values of y. So that means this is the boundary, y equals 0. And if y has to be less than or equal to x, first of all, we have to understand where is y equal to x. What is the boundary of this region? Y equals x, okay? Is this line? Y equals x. So if now I know y equals x on that line, where, for which points are y values less than x?
Lower part.
For every x value, on this line, y and x are equal. But if I take this x value and I say, okay, y has to be less than x value, it has to be below that line. So actually this will be the domain. So we have two inequalities and we have to sketch them on the plane and we have to look at the common region that corresponds to both inequalities. So to solve such an inequality in two variables, first of all, you have to find the boundary curve or line. You have to look at the equation to sketch the curve, to sketch the boundary. And then you have to look at the inequality and figure out which points we need to choose. And that sometimes it can be a little bit messy, but generally if you have sketched the boundary curve, it's not so bad. For example, number 2, x squared plus y squared greater than or equal to 1, less than or equal to 4. It's a ring. It's a ring. X squared plus y squared equals 1 is this square. But if x squared plus y squared has to be greater than 1, then it's the outside of this square. Circle. So this corresponds to this inequality. Now if I want to look at the second inequality, which make me, I can agree then. Okay. The second one would be a circle with radius 2. Because x squared plus y squared equals 2 squared. And if this has to be less than 4, then it means the points are inside the circle. So like this. And now all we have to consider is which part of the plane has double shading. Which part of the plane corresponds to both of these? Obviously, the part of the plane outside of this circle and inside this circle. So it's a ring, like this. A ring, inner radius 1, outer radius 2. So the domain is this ring. I won't say donut because donut is a three-dimensional thing. But a ring, yes. Next one. So I'm going into this very carefully. Surprisingly, finding the domain seems to be more difficult than differentiating two variable functions and finding partial derivatives. I don't know why exactly that happens, but all right. So number 3 for 3. X is between 1 and 2. So if x is 1, it's this vertical line. X is 1. X is 2. Oh, no, there. X is 2. This vertical line. X is 2. So x is between 1 and 2. All right. So these points, all these points between these two lines correspond to the first inequality. Now the second, y is less than or equal to x. So on this, okay, I have to use the other one. So y is equal to x, y is equal to x on this line. So if I have to write y is less than or equal to x, it will be below this line, right? Y is less than x below this line. So it will be going down, 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 down. I'm not shading the whole half plane. I'm simply shading to show the direction where it goes. And y is greater than or equal to 1 over x at the same time. So I have to sketch the function y equals 1 over x. So I have to do 1 is greater than or equal to 1 over x. So first of all, 1 is equal to, y is equal to 1 over x. That's the hyperbola passing through the point 1, 1, 2, 1 half. So it's this hyperbola, y equals 1 over x. And then of course we have this other side, but it obviously doesn't matter because on this side we don't have the part that matters. And y has to be greater than this. So we need the points that are above this curve. If y has to be greater than this, we have to go upwards. So it would be like this. So now we can see the actual domain. It's this part. So straight segment, the segment of a curve. So this is the domain. This is the domain. A very small bit of the plane, but if this is defined, the function is not defined anywhere else. Number 4, x between minus 1 and 1. All right. So where were we? X is between minus 1 and 1, so it will be here between these two vertical lines again. Hold that understandable. Now, y has to be less than or equal to 1 and greater than or equal to x squared. So y is equal to x squared. Well, obviously on the parabola. This is 1. And less than 1. So if y is greater than, on this curve, y is equal to x squared. So if y has to be greater than that, we need to look above the parabola. So we have to go upwards from the parabola, and then y has to be less than 1, or less than or equal to 1, like this. So we go down from this line. So we can see it's this part. It's this part of the plane, this part of the whole thing. Obviously, the first part about x was not so necessary, really, because we still did the same without the limitations for x. But sometimes functions are like that. That you see that perhaps some parts Some parts don't do anything for the domain, and some other parts are more important for the domain. So this exercise gave you the conditions for the domain explicitly. They were just written down, what inequalities you had to fulfill. In exercise 5, you have a function, and you have to figure out what the domain is, what the inequalities are, what the constraints are actually. What are the conditions? For example, if we have z equals arc sine of x plus y, and now we have to figure out what the domain of this function is. So, we have to understand, we have to remember what is the domain of arc sine function? For what numbers are arc sine values defined at all? Arc sine, the inverse of sine, which means the domain of arc sine is the range of sine function. Remember, if two functions are inverse, then what is domain for one function is the range for the other function. So if I need to find the domain of arc sine, forget x and y, simply the domain of arc sine. For what numbers can we find values of arc sine?
From -half to half?
From -1 to 1. Because arc sine is the angle for which this is the sine. And sine can be only from -1 to 1. Which means we have a condition, x plus y has to be less than or equal to 1 and greater than or equal to -1. Because the domain of arc sine is from -1 to 1. And now we have a condition, which means x plus y has to be greater than or equal to -1, or y has to be greater than or equal to -x minus 1. That's one condition from the left-hand side. This is from this. And from the other side, from this, I can write x plus y has to be less than or equal to 1, y has to be less than or equal to -x plus 1. Two parallel lines, -x minus 1 and -x plus 1, two parallel lines, and y has to be between them. So, -x, that would be the diagonal of the third, of the second and fourth quadrant, plus 1, so if I have 1 there, this line at 135 degrees, right, this is the line, y equals -x plus 1, and if y has to be less than this, we have to go downwards from there. Now from that side, -x minus 1, so it's -x minus 1, we go down, -1, it's this line, they are parallel. Okay, it's -1, I suppose. And y has to be greater than this, so we have upwards from this line. So obviously the domain for this function is, again, the region between these two parallel lines. And that can be found from the domain of the function, from the domain of the simple function. So we have to write down the constraints by ourselves. It's not as if they are given already. In exercise 4, they were given. In exercise 5, we have to figure them out ourselves, understanding the domains of functions. And the only thing we can do to depict the domain is simply sketch. Simply sketching is the only way of actually solving the domain, finding the domain. Ln of xy. That's the next one. Z equals natural logarithm of the the product xy.
Must be great.
So xy has to be positive by all means. xy has to be positive because logarithm can be found of only positive numbers. The domain of the logarithmic function is the positive numbers only, real numbers with only positive real numbers. Which means, so how can we know when is the product of x and y positive? If both x and y are positive, it's the first quadrant, and that's all. When is the product of two numbers positive? 6th grade.
When both of them are negative.
When both are negative.
Or both positive.
Both negative or both positive. So both positive, first quadrant, both negative, third quadrant. By the way, they cannot be equal to 0, but strictly positive. So this means we must exclude 0, so I'm putting the dashed line on the axis, because the axes themselves don't count. Two quadrants, but no axis, like this. This is the domain of that function. X plus arc cosine of y. That's simple actually. Z equals x plus arc cosine of y. X can be anything, no restrictions at all. So we understand that arc cosine, the domain of arc cosine is again the same from -1 to 1. So this means that y has to be between -1 and 1, and the domain is simply depicted. Two horizontal lines and the area, the region between these two lines. It's not exactly accurate to say, to call it the region, but still. So it will be this. Y equals 1, y equals -1. So the part of the plane in between these two parallel horizontal lines is the domain. So x has no limit, so any values of x are good. And our cosine. So this is actually a good revision of some functions and properties of functions. You always have to keep in mind properties of functions, because yes, we did discuss the functions and everything in the first semester, and now I just must assume that you know functions, you understand functions, you remember at least the domains and the general shape of the graphs. All right, number 4.
Get this, that's great.
Wow. Oh, not for me.
No, I was just asking about the grades of the test.
Oh, right now I don't have them. Right now I have Wednesday in my head.
Oh yeah, okay, no, I mean like, did you correct the test or?
Yes, I did.
Ah,
Too many fails. Please tell your friends who don't attend lectures not to come to test. They sit there, they know nothing, they cheat, they simply make me angry and spoil everybody's work. There were really lots of fails. Which is why I tend to remember more or less the people who did not fail. Few of them. All right. So I'll bring them on Thursday. Of course, you can try emailing me and asking me, but I'm extremely busy these days, so it's easier for me just to bring them on Thursday, to bring them out for you on Thursday. Tomorrow I won't be able to answer because tomorrow my day is packed full from early morning to late evening. So I won't have time. I simply won't have time to reply to emails. Okay. Number 4. Z equals square root x plus y ln y squared minus x squared. Now this. For the square root to exist, x plus y must be greater than or equal to 0. For the logarithm to exist, y squared minus x squared must be strictly positive. So now we have to solve this. Now we have to solve this. So what is there? We can think like this: x plus y greater than or equal to 0. Y minus x times y plus x has to be greater than 0. So from this, what can we say?
That x minus y also must be greater than
Yeah,
0.
y minus x, yes. Y minus x must also be positive because we already know that this is greater than or equal to 0, but it cannot be equal to 0. So from this we can say x plus y must be greater than 0. It cannot be equal because of the second inequality. It cannot be equal, and because x plus y or y plus x is the same is positive, the other factor y minus x must also be positive. So we just simply slowly think logically. We simply think logically. X plus y must be non-negative. But looking at the second inequality, we see now it cannot be even 0. It has to be strictly positive. It cannot be 0. So yes, it's strictly positive. If this is positive and the product is positive, then the first factor must also be positive. Which means y has to be greater than minus x and y has to be greater than x. Which means what? Y equals minus x, it's this. Y equals minus x. I'm actually assuming that you understand why can I sketch the line exactly, immediately. I know what it looks like. You should do, but who knows. Okay, y is greater than minus x, so it's above this line. And then y has to be greater than x. Y equals x is this line, and it has to be greater than this, so it's above that line. So now we can see the actual domain. It is this area, this part of the plane, not counting, so the right angle actually, but not counting the sides of the angle, only the inside of that right angle, because it's strict inequality, equality is not allowed, so these lines themselves that provide equality don't count. So it's simply this part. So this takes some logical thinking. If not, then you would need to find some manner of solving this inequality and depicting this inequality separately, and that would be rather messy. That would not be pleasant. So it's better if you can think logically and simplify it and simplify it and simplify it as much as possible to make it easier for you. 5. What a beauty. Isn't it nice? So number 5. Z equals 1 over square root 4 minus y squared minus x squared plus logarithm of x squared plus y squared minus 1. It's actually very nice. First of all, 4 minus y squared minus x squared must be strictly positive. It cannot, in this case, it cannot even be equal to 0. Why? Normally, under the square root, I would write greater than or equal to 0. Why am I not writing equal to 0 now?
We cannot divide by 0.
Cannot divide by 0. And from the logarithms, of course, x squared plus y squared minus 1 has to be strictly positive. Now we see x squared plus y squared has to be less than 2, and x squared plus y squared has to be less than 4, sorry, and greater than 1. So it's again the same ring, but this time it's without the circumference curves themselves. Only the part between the two circles, between the two boundaries. So in this case, it has to be like this. 1, 2, 1, 2. Only this part between the two circles, but not the boundary lines. Number 6, I like that one.
Number 1?
Now 5, 6. Exercise 5, number 6. Some people are becoming impatient. Okay. No problem. Number 6. Z is square root y sine x.
In the previous example, we
What did you do?
the boundaries of the ring.
No, because strict inequality, it does not allow equality, so we don't count them. And if we don't count them, we simply depict them by dashed lines. We have no other way of showing that the boundary lines don't count, other than dashed lines. Now, this is very nice. Now this is very nice. So we understand that y times sine x has to be greater than or equal to 0. We know that sine x can be positive, can be negative, can be 0. And obviously if sine is positive, then y must also be positive or 0 or 0. And if sine is negative, then y also must be negative, because we have a product of two factors. And if we need this product to be positive, then both factors must be either both positive or both negative. So y is, I'll start with sine actually. Sine is greater than or equal to 0, and y is also greater than or equal to 0. This possibility, or sine x is less than or equal to 0, then y also must be less than or equal to 0. I absolutely love this function. I absolutely love this domain. So now, in order to understand what's going on, I am going to sketch the sine function just a little bit, so that we understand what's going on there. So obviously, like this, and so on. So this is pi, this is 2 pi, this is 3 pi, this is obviously 1. That doesn't matter, 1 doesn't matter. But these values do matter. Minus pi, minus 2 pi, the next intersection point, minus 3 pi, and so on. Because now, for those x values where sine is positive, and we can say sine is positive here, sine is positive here, sine is positive here, in these areas, y has to be greater than or equal to 0. In other words, for those x values where sine value is positive, for these x values where sine is positive, y also must be positive. So actually it would be this part, right? Because sine is positive, for these x's, y must also be positive, or 0, of course. Now, the situation repeats itself here, here, and so on. Wherever the sine function is positive, for those x values, y must also be positive. What happens when the sine value is negative? Here. Y value has to be negative, or 0, of course, or 0. So it's this part, and it's this part, and it's this part, and there's this part, and so on, like a crazy chessboard. But it takes some thinking to get to this. It's not obvious from the first. It's not obvious from the first. You have to think. You have to think. So this is okay. I would say interesting for me.
Yeah.
It's just like playing with functions, playing with x and y values. Actually solving systems of inequalities or inequalities in the plane for two variables is quite interesting.
So we have just a sketch. This graph it shows the domain.
I sketched the graph not because it's the graph of the given function, it's not. But I sketched the graph of the sine function simply to see where sine is positive. Simply to see, to make it more obvious. I did not have to sketch the sine function. I only sketched it to make things obvious, to see why did I go upwards. Because sine is positive here, the condition says if sine is positive, y must be positive for those x values. For those x values, yes? So we do it. Okay, how do we find the limits? Lim tangent of xy divided by y when x tends to 3, y tends to 0. This? I like this. No. Remember the basic trigonometric limits? We had sine of t over t is 1 if t tends to 0, but at the same time tangent of t over t is 1 if t tends to 0, arcsine, arctangent, and so on.
So we may divide and multiply by x?
Yes, exactly. Exactly, just like we did before. So now I can think of this as limit when x tends to 3 and y tends to 0 of x times tangent xy divided by xy separately. So I understand that this actually tends to 1, x tends to 3. So it's 3 times 1, it's 3. Or I could do it as two repeated limits. I could do this as repeated limits, of course. I could take, for example, first x tends to 3, and then we would have 3 times tangent 3y divided by 3y, and after 3. Or in the other order.
So that must
Basically, it's.
There must be y tends to what, to 0.
Yes. Because y tends to 0, we have this. Second limit. How much time is that? A little bit. Just for the limits. So the number 7 is next week. Limit x tends to 0, y tends to 0, 2 minus square root xy plus 4 divided by xy. 0 over 0. How did we solve that kind of limits?
We took separate.
So this is basically very similar to 2 minus square root of x plus 4 divided by x, because if both of these tend to 0, then the product tends to 0, of course. What did we do in this case?
We take two parts, limits.
We multiplied and divide by the conjugate. By the conjugate. So 2 plus the square root, 2 plus the square root. So the same method, the limits, for the limits, exactly the same methods work. Just the same things we did for limits in one variable. Basically, the same methods can be applied. Only sometimes when we have a feeling that this limit might not exist, we do the repeated limit. Now, in this case, we have 4 minus xy plus 4, the difference of two squares, 2 squared minus square root squared, divided by xy 2 plus square root. This 4 minus 4 disappears. We get minus xy there. So it's lim x tends to 0, y tends to 0. Minus xy divided by xy times 2 plus that square root. These two cancel out. So now we have minus 1 divided by 2 plus square root of 4. 2 plus square root of 4, which is minus 1 over 4. So the methods are familiar, hopefully. The methods are exactly the same. The difficult part is probably to look at two variables and recognize the same pattern that we have already done many times with one variable. That's probably the difficult part, is stepping up to the next level to two variables. Because the general idea, the general patterns are always the same. As you may have noticed, mathematics is not really about numbers. Mathematics is about patterns repeating and repeating and repeating themselves. And descriptions of those patterns. 3. Whoa. Should be something similar. Number 3 should be something similar, so we can leave it for now, because it will be done exactly the same way. You multiply by the conjugate of that upper expression. And number 4. Do we want to do number 4? It's again something very similar. It's 0 times something bounded, so it's similar to to example C, so we don't have to do it really, because it's done exactly the same way. All right. Go home, study definite integrals, scare away your